是测试 test one two。有
喂，喂， 先开始吗？学会学术讲演讲即将开始，请各位贵宾尽快就座。The special lecture by the TMS Academic Prize winner will begin shortly. Please take your seats as soon as possible. 请大家注意，本演讲厅内是禁止饮食的。Please note that no food or drinks are allowed in this lecture room. 各位嘉宾，接下来是学会学术演讲时间，让我们欢迎主持人王正南老师。Ladies and gentlemen, we will now begin our special lecture by the TMS Academic Prize winner. Please give a warm welcome to our chair, Professor Zhennan Wang.
No, for him, not for me. Okay, it's my great honor to introduce the speaker, the recipient of Academy Award this year. And Shi Xuan currently is the Distinguished Research Fellow at the Academia Sinica. I'm not gonna introduce his educational background. It's just too cliche for a great speaker like Shi Xuan. So I'm gonna tell you some of his characters. Shi Xuan has a strong affection for Taiwan. And his love for Taiwan is beyond everything, even his wife. And he has been wandering around out of Taiwan for maybe almost 2 decades. And ultimately, he returned to Taiwan, the place of his academic journey began. And he vows to devote himself to fostering young scholars and to educating students. I would just like to quote Isaac Newton's famous words. Isaac Newton once said that, "If I have sinned further than others, it is by standing upon the shoulders of giants." And I don't have the privilege to stand on the shoulder of Shi Xuan, but I think other people certainly can. So without further ado, I will give the floor to Shi Xuan.
谢谢 ，OK， 多谢啊，我的名字叫做我是游世贤 ，OK， now I speak in English， OK， thank you for the the society offered me this opportunity to deliver this talk. And now I'm giving the talk. This is actually the long journey with Taiping on the journey of the green function. Okay, so the title we today here, the green function and the linear and the nonlinear wave motion for compressible wave motion. And I'm been aware many people are not familiar with the PDE. So I will give a very plain language from very elementary, maybe even the undergraduate student can appreciate a little bit. Okay, now, so first, I will say here, what is the compressible flow? The good example is the gas flow in our room. This is so this is the density of gas. Okay, this is the flux. Okay, this is the velocity. Okay, so so the first equation is the conservation of mass. Okay, and this is density, velocity. Okay, then this is conservation of momentum. Okay, and this one is the kinetic energy, and this the pressure. Okay, you can say this energy. So actually, the flow in our area is governed by this compressed flow, and now the equation looks very simple, but it's very complicated. Okay, so now let me say here, the reason we say is, okay, so this is a quick example of compressible nonlinear equation, and this form is called the conservation law. So now let me tell you what is the meaning of the conservation law. So for example, so here, this is some physical state in the pipe, okay? And so now example, for example, if some people want to give making your body fit, okay, you are very concerned about your body weight. Okay, so now you can think, okay, so you can think this is your body weight, okay? And then so now they say here is the change rate of your body weight. So okay, so now the change rate, it depends on how much you eat too much, your weight will increase. And in the same time, you need to do some exercise to burn your calorie. Okay, so that means that the change rate of your body weight is corresponding to change rate of how much you eat and how much you consume. Okay, so this is the very simple way of the change rate of your body. And now it's quite simple. If you take the ratio of this delta x goes to 0, then it simply, the equation, it becomes this form. So this is universal. The conservation law, it comes in this form, okay? Now, law, this is just an equation, but the equation itself has a spirit. It will move. And then now let's try to realize that what this equation, okay, what this conservation law tells us. Okay, so now they give me some simple example. So now, if I look at the conservation law of this form, okay, so then you can think, okay, so we call this one the transport equation. So this means that, okay, it's just like you take a U, it's like a profile, and then the motion are governed by this conservation law. It just means a translation go like this one, okay? So this is very simple, okay, linear conservation law. Okay, now let me give you another example. This is like the temperature in the space, okay? So this one, so here, you say here, this U is the distribution of the temperature on a pipe, okay? And now according to the Fourier, you say, okay, the heat flux is moving from the opposite direction from the high, it moves from the high temperature to the low temperature. So this means, okay, the flux of the energy is in the negative side of the temperature gradient, okay? So the flux is defined by this one, okay? Then you can derive the famous equation, the heat equation, okay? So that's okay. So the change rate of the temperature is proportional to the gradient of, okay, the gradient of the temperature gradient. So you got the heat equation. Another good example is the vibration of the string, okay? So okay, and we see the okay. So now this one is the displacement of the string. Okay, and now you suppose that this variation is very small. Okay, and now you will derive the wave equation. This ln t square is equal to c square ln x. And now here, this is c square is the wave speed, which is equal to the tension divided by density of the string. So this means you pull stronger, and then you see the string is with the speed of the. Okay, sorry, it's just okay. Okay, so so it means that so if a higher tension, okay, and the low density, then it's the speed of the wave it move faster. Another good example is the famous Schrödinger equation. But for the Schrödinger equation, the conservation law is given in the other form. Okay, this is by the Broglie. Okay, he said the energy, the total energy is the kinetic energy plus potential. Okay, and Schrödinger is write this form. So this means that the conservation of all the wave equation is so important. It appears everywhere. So what I mentioned to you is just for the linear equation. Okay. Now, okay. And now we say, okay, and the linear equation, there is, okay, is a system of equation. Okay, so now if we want to model the motion of the sound wave, okay, then we need to introduce a system of equation. And for all this light and the electronic we see in our real life is by Maxwell equation. Okay, and there are also some other important equations like the motion of the Earth. Okay, there's the linear elasticity. Okay, so this displacement. Okay, here this is the mechanical property of by the Lamé constant. Okay, so here, though this linear equation, you can start use the system of equation to model the law of physics. Okay, now let's look at something burst the linear equation. Okay, so now let's look here. There are also some other simple nonlinear. Okay, so now here we look at this nonlinear equation. It means equation is a coefficient depend on the solution itself. Okay, so this is the famous equation, the Burger's equation. And now, okay, here I write two examples. Okay, so for this nonlinear equation here. Okay, so now if you say your initial data like this one is a monotone decreasing, okay, then here this is t equal to 0. And then when time evolves, it will go, this one go a little bit closer to here, this one go close to here. So this one is it gradually compress itself. And up to some moment, it forms a shock wave. Okay, so for the Burger equation here, if the profile is a monotone decreasing, and we call it a compressive. And they see here the nonlinearity cause a shock wave developed. And now, opposite this monotone decreasing, and now you look at the scenario is a monotone increasing, the behavior is completely different. So this one in here, the wave moving toward this direction, and it move toward this direction. So it start to expand. So then for this problem, there is no shock wave happening. Okay. So now we have some good example that about the linear wave motion and the nonlinear wave motion. Okay. Now I'm going to tell you that in the topic of the title, the Green's function. Before I want to talk about the Green function, let me tell you something that that happened in all this notion. So here this H, X is called the Heaviside function. It's very simple. You just say the function is 0 here and equal to 1 here. Okay, so it's a function of two values. We call the Heaviside function. And why this is so important? Because I'm going to use this one to define the Dirac delta function. Okay, so you take this Heberside function. Okay. So then you look here. This function is a constant here. It's a constant here. So this derivative here is equal to 0 if x not equal to 0. Okay, and now when the x equal to 0, it brought up infinity. But okay, but now let's check what the property here. So okay, if I replace this delta by Heberside function here, you integrate out any continuous function with compact support affinity, and then you got this property that okay, the delta function multiplied f of x is equal to this one. Okay, so we use the notion of this Heberside function to define the delta function. Okay, now with this notion of delta function, okay, then we define what is the meaning of the Green's function. Okay, the Green's function means what? Okay, so we need to have equation. So first, okay, say take this p is any polynomial. Okay, and so here this is a differential operator. So let's define a differential equation. So this means when we want to talk about Green function, we need to have a differential equation. Okay, so our definition of Green function is a solution of this differential equation with a very spatial initial data. Okay, so now this is our definition of Green function. Sorry, can you help me here? Okay. Okay, so okay. So now they check. Okay, so now they check this function. Okay, so now we say when t equal to 0, this is the delta function. So by our definition there, okay, so let's mean that this integration give you is the initial data. Okay, so let's mean okay. So now I multiply this Green function with initial data here. Then this function it give you exactly the initial data. Okay, and the second here that okay. So this function, you apply the differential operator under this g. So when this one is moved back to here, this 0. So this means that this function, okay, so this means this function solve this differential equation and solve the initial data. Okay, so now with this Green function, we define the solution of the initial value problem. So now we can realize, okay, so we write the notion of Green function in another way. So this means that, so we think, okay, we can write the Green function is means the kernel function of this operator. Okay, so this means that, so you can think it like if the people doing the Schrödinger equation, okay, let's evolve is an evolution operator. So you can say here, the Green function is the kernel function of your evolution operator. Okay, so now with this notion here, okay, I want to introduce some good term of the Green function. Okay, so now you back it to here. Okay, so now let me just give you some other good example. Okay, so now if this one is the transport equation, okay, we know, okay, so then the Green function is simply just like a delta function in this form, okay, and for the He equation here, the Green function is given by this Gaussian. Okay, so this one you can check in any textbook. We have this one. Okay, so now we want to see, okay, how to use the Green function, okay, as the input and output. Okay, so now let's go back to in our calculus class. When we look at an ODE with inhomogeneous term and with this initial data, and for this ODE, okay, then the integration factor is at the e to the minus at. Okay, so okay, we multiply the integration factor to this ODE. We got this one, then we can represent the solution of ODE as okay, exponential at multiplied with initial data plus with this input term. So now, if you think in this picture here, you can see, okay, the solution here is the contribution. It can starting from initial data, give you from your initial one, and then you have input at the time tau propagate through with this time lag to this position. Okay, so then by this integration factor, we can write down the solution for this inhomogeneous ODE in this form. And now, so now we replace this one by the differential operator. Okay, then we can write the formally the solution of this PDE with this inhomogeneous term at this form. Okay, now we translate this one in the okay. So now we replace here with the x. Okay, so then this one you write the green function. Okay, and the multiple and this one we write as the kernel function of green function. So we write the Duhamel principle for the PDE with a given inhomogeneous term. Okay, now I give you some example. Okay, with the PDE, okay, we know the green function with this inhomogeneous term. So here, this is a transport equation. So this y is mean all this green function here is a delta function go around to here. Okay, so now if x is outside this region, so it go back to here. It only touch the initial data. It do not touch this input term here. So you got it. So you only have this one here. If x between this region here and this one you integrate it here, you create an extra term is a 1 over the difference of the speed. And now if x outside here, it touch nothing. Okay, so here you see we can see the PDE with the inhomogeneous term. You can have very precise structure of the solution. Now, if we want to handle nonlinear problem, okay, so now we can use the Duhamel principle to represent the solution in the list form. So you can write as a 1, okay, the contribution from your initial data, okay, and you put this one as an inhomogeneous term. It got the input, okay. Now what I'm trying to say here, if you know the precise structure of your kernel, okay, and the precise structure of your initial data, and then you can use the information here to create an answer and plug into this nonlinear term and the core and the couple with this kernel and put around here, and then you can develop a bootstrap procedure. You might able to find the precise structure of the solution. Okay, so now I give you an example. Okay, so now if we look at the Burger's equation, okay, so we look at the Burger equation, and we know that say here this hypertangent, this is a solution here. Okay, so if we want to solve the stability problem of this one here, okay, then we just simply just do this. Okay, take V as the perturbation. Then we got the equation. This is the nonlinear problem here, and here this is the nonlinear term. Now we know the green function for this part is given in this form. Okay, so we put into the answers. Okay, so we put it in here. This answer by the Duhamel principle. Okay, this structure is due to we know the green function here. Okay, so from here we can get the structure. Okay, we can find some structure here and the input to here. As long as this is so small, then you finally you can conclude your nonlinear problem is got a very strong estimate. Now all this thing here is based one thing here. You need to know the precise structure of the green function, okay, no matter what. Okay, we try to get the structure of the green function, okay. So now Now let's start to think, okay, how to see the structure of the green function, okay? So now say here, let me give you the example here. Say this P is this differential operator is a polynomial only, okay? Then this problem, okay, we can do it by, okay, we take the Fourier transform, then then the spectral representation here, it becomes the exponential to the polynomial, okay? And then we can apply the inverse Fourier transform. Okay, so we say here, if this differential operator is given by this one, is a spectral like this one here, okay, by the inverse Laplace transform, got this one, and the whole equation, you got this one, okay. So now, this is the case, okay, when this one is a polynomial, we can do it. Now, let's look at, is the Fourier transform, is so powerful? Okay, this is a question. So now let's give you an example. So now if I take the differential operator of this form. So here, this one is corresponding to the linearized Navier-Stokes equation. Okay, so now, so we compute the differential operator is a Fourier transform in this form, okay? And then we apply, so we can compute its this exponential in the transform variable. So we can have this spectral decomposition. Okay. Now I want to say here, so we can compute the green function in the spectral variable explicitly, fine. But now look here, the spectral is going in this form. So now look here. For the Fourier, okay, eta square, fine. But this one, okay, here, this function is not analytic. You got the trouble with the Fourier, okay? So, so now we got this, okay, so now we see, okay, how we fooling around with the Fourier variable of this one, okay? This is question one. And the second one here, that if you choose, okay, if you choose here is a plus sign, okay. If you choose this one, the plus sign, and then when eta goes to infinity, this value goes to 1. And then now, okay, so this value goes to 1. And then now here, this one, if the Fourier variable, when eta goes to infinity, do not decay. It means it's a singularity. Okay, so now we need to handle around, okay, all this singularity due to, okay, analyticity one, and the second is that this one and this one cancel out. Okay, it creates a singularity. How we will do this one? So actually, like a mathematics, we need to look at infinity, what the singularity. Okay, so now the stage one, okay, we call it, okay, a singular regular decomposition in the Fourier variable. Okay, so now we expand this function at the infinity. Then we can expand. Okay, take the finite expansion, and so now all this function here, it approach to original one at the infinity, very high accuracy. So okay, and okay, so now we use this one to take care the singularity. And now the reason we need to do this one is that, okay, when you took this one here, it becomes the Yukawa potential. You can perform the inverse Fourier transform of this one. And this one also sufficiently tell you the delta function. You just look at this component and this component. When the x to infinity, it converges to number 1. So okay, so now, so this one combined together, it tell you the exact structure of the delta function. Okay, so now you see here that this is not like a Higgs equation. Look, everything is regularized. In here, in this component, it remain as a delta function, but decay in time exponentially. And plus the other thing here, decay exponentially in the space and time. Okay, this is the first one. Okay. And the secondly, are you sure that this is a good approximation to your problem? Okay, so then, okay, we need to plug in. Okay, so we need to plug in the equation. Okay, so here, this one is okay, sorry. Here, this is your approximate, okay? Your approximate spectrum, and the plug into the equation, okay? And then, because you choose this, it approached at the infinity with a sufficient rate. So this one, it give you that, okay? Though this one has a singularity, but this one cancel out. So this one becomes smooth. Okay, so then it turns out, so this means that this function, it catch up all the singularity you required. And also the everything, okay, the truncation error produced by this one, it decay in the space, okay, it's in the space and time exponentially, okay? So we plug in, okay, this is truncation error to the original upper semigroup. Okay, then you create this one, we call it the regular parts, okay? So this one has a sufficient regularity structure, and by complex analysis, okay, then you can see the structure of this one is concentrated around the some kernel. So this one, you have a precise structure, and this one give you good structure of singularity. So you put together here, so you synthesize the kernel function with someone carry all the singularity, and the other one keep you this long way structure. So here, this is the example to demonstrate how to constructing the green function. Okay. Now, okay, I will tell you, okay, some other operator you might interested. So okay, so now here, okay, here this one, okay, say this one is the Boltzmann equation here, okay, okay, and for the Boltzmann equation, this one is the collision operator, okay. Now, for the this Boltzmann equation here, when the F equal to this form, we call this is a equilibrium state, okay. Now, if we choose, okay. So now we choose this equilibrium state is some special, okay, actually it's quite general. We look at this equilibrium state, okay, and then we linearize the Boltzmann equation around this Maxwellian state, okay, put this some weight. So we got some new linear equation, the new linear equation, okay. Okay, so now we call this one is the linearized equation. Now, okay, about this linear collision operator, okay, here, okay, study is very clearly, okay, he say this is a linear collision operator, you can write as one part is the dissipation part. And then, okay, and here, this arrow have another part is K, is the integral operator type of structure, okay? So now we want to look at how to construct the green function for this linearized equation. Okay. Now, this is not an easy problem. Okay, because this K is an integral operator. Okay, so this you have a transport part, and and you have this K is an integral part. It's not easy. Okay, so now let's have some view to see this linearized equation. So now, regarding to, so now if we treat the differential equation as the initial value problem with the transport part. Okay, so here, so that means that this is the initial data. Okay, so we try to see the green function as an equation with a spatial initial data at the delta function. Okay, so then by this transport part, you will see the solution, you will contain a singularity propagated in this line, okay, and with something others, okay. So so now this is the picture we have if we treat the problem as the transport equation. And now on the other hand, if you view this one in terms of its spectrum, as a spectral property, and then we can compute the eigenvalue of this operator, okay, in terms of this wave number eta. Okay, then we can compute if eta within some range is a spectrum is a line on here, but we don't have the information outside here. We only know the information lie in here, okay? And so here we have two pictures. These two pictures are not complete. That for this one, we don't know how all this line here. And for this one, we only know this only finite information about spectrum. How do we put them together? Okay, so now we look here, the next picture. Okay, so now, because this one is like okay, so now you write the linear acquisition operator like this ODE and this here. Okay, so now you just perform one thing here. So you do like the problem like ODE, you do like a Picard iteration. Okay, just with some modification. Okay, so you can write this PD, okay, as ODE with a finite, okay, X series, okay, just like doing the Picard iteration. You're doing like this right here. Okay, here I need to do some modification. So let's say I define this one, okay, only as a particle-like, okay? So now I will say here, so since here I put it a finite, so every term here decay in the space and time exponentially. Okay, so first here, this particle part have this one. And the second, we invent a mixture lemma. Okay, that means that if you take the green function, take out this particle part here, we can assure that the remainder term part has a certain regularity up to how many terms you put in here, okay? Okay, so now you do something, okay, quite good. Here, you have very precise structure, but the remainder, you don't know. You only know it have a regularity only on the Sobolev space, this first one, okay? And okay, so now this is the first picture we together here. Okay, so here we gain this regularity. And the second here, on the spectral here, okay, then okay, we write the green function at the two parts, long weight and the short weight. The long weight means you take only the spectral information on the finite Fourier number. Okay, you integrate out here. Okay, now the beauty of this one is that, okay, that here, that everything in here is analytic under this Fourier variable. Okay, so you can apply the complex analysis to find the structure here. And now at the outside here, all the spectrum is outside here. So this operator, it's allowed two operator decay exponentially. So you put this regularity property here and this smooth information, okay, this is a smooth structure here. Eventually you can write down the green function of the linear equation is just constant under this range, okay, like okay, so it behaves like a Gaussian here, and outside this region decay exponentially, okay. So now we got the precise structure of the green function of the linearized equation, and now okay, so now with this precise green function here, we can apply the green identity to show that okay, if the problem is a problem with a boundary, okay, then you can use this one here to construct the green function with the boundaries. Or in here, I need to say here this b not equal to 0 or 1. Okay. Now, also this identity, okay, it can help us to do the center stable center unstable decomposition of flow. Okay, so now we take the Maxwellian like this one here. So for any given data there, we can split into three parts. Okay, so here and here this B now called the center, which one is on the kernel of the linear collision operator. Okay, so we can bring any data given. Okay, we split into three parts, and here. This B1, B minus, and B plus, it can define a layer. Okay, so here this data, okay, this data, okay, you will define a boundary layer toward infinity, and this B minus will define a boundary layer go to the negative infinity. So okay, and so here, and this B plus B minus is through the green function. of this equation with a damping. You put some damping here, upwind and downwind damping. Okay, and you integrate your green function with this given data here. You integrate out. Then you can construct this B plus B minus. So with this construction, you define the decompositions to the center, stable, unstable. So then you can use this structure to define the invariant manifold for this steady Boltzmann flow. Okay. And now that, okay, I will tell you more info advantage of this green function. So, okay, so now if we consider the Boltzmann equation here with the initial data like a Riemann problem. So you put here the initial data here to put some Maxwellian and some other Maxwellian at t equal to 0. Okay, and now you remove this membrane and how the gas spread out. Okay, so of course here this is singularity here. It will propagate into the space. Okay, so now we use our green function. Okay, we bring the green function into the particle part and the wave-like part. Okay, so we use the Duhamel principle and to rewrite the Boltzmann equation in the singular part and the regular part in this form here. Okay, now here this H is the Heaviside function. I just tell you to use it to define the delta function. Okay, so now that by this initial data here, okay, you can write so we can assume the initial data is the Heaviside. Okay, yeah. So we assume the solution here is in the form Heaviside multiply some function is independent of x. Okay, so this means so we say the particle part is like this one here plus something is bounded. Okay, and now what you would do here, so you apply the x derivative to this equation here. So you rewrite, so you put this one here. Okay, then by our green function, okay, then you get here on the left hand side, you delta function times this one here. And this part here, you create a delta function and this here, and here there's some coupling term. So it turns out what you can see here. So eventually you balance the delta function, okay, of this one. So you got the equation A here, and here you got, okay, so this one from the initial data here, and from here you create some coupling term. So eventually you can prove that the singularity is like a scalar equation. Then you can prove the propagation of the singularity. Okay, now we go on. Okay, also still on green function. Okay, so now I'm just departure. Okay, from the Boltzmann equation to something. Okay, we got familiar. So now if you want to look, okay, so now here I have heat equation. Okay, and with the coefficient is say the very rough coefficient. For example, it's like say here is like some step function like this one. Okay, so then the heat conductivity is not uniform. Okay, and now so now at every discontinuity, then we can using the heat conductivity on each side. Okay, we define the reflection coefficient at this continuity, and we define the transmission coefficient under this jump. Okay. So now we see in this picture here. Okay, we can assign all this data here. Okay. So now we will see how we can solve this heat equation with a very rough the coefficient of the heat conductivity. Okay, so now the procedure is like this right here. Okay, this is the equation. Okay, the initial data, you take the Laplace transform with t here, then this PDE, it becomes this ODE. Okay, so this one is due to the initial data. Okay, and this one it becomes the PD becomes this ODE. Okay, so now first, I'm say here for everything, okay, regarding to the, if some function of this form is regarding to the Laplace transform of the Gaussian, okay? So now I'm going to use this one to synthesize the solution for this one, okay? So now look here. So here I got this, the R is the reflection, T is the transmission, okay? So now I introduce a notion. Okay, so now, oh yeah, okay, just a moment. Okay, so now here we want to, okay, so here, look here. So here, this Y is the, okay, this Y is the location of your delta function. Okay, X is the position you want to solve, okay? So here you have parameter Y and X, okay? So now we introduce, okay, so here this is, all this grid point is mean the discontinuity of heat conductivity, okay? And okay, so now here say your position of your initial data. X is the solution of your as X, okay? And so now we define, okay, so given Y and X, we define the path, okay? So that means that all the paths you go from Y to X is only allowed to change the position at the grid point, okay? And so now, if we go like this one, this means the transmission, okay? And if you go like this one here, this means this is a refraction, okay? And so now, so then you can, at each point, okay, transmission, transmission, refraction, transmission, 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 transmission. Okay, so we take the product of those data together. We define this one as a major of this path, okay? And now we also define the phase of this path. It just integrate your path. Okay, you just integrate this function along your path. This define your phase. Okay, and now we say that the solution of your heat equation under this Laplace transform, it can written as this formula. Okay, so this is like the Feynman path integral formula. Okay, so you can see this is the path integral, and this one it defines the major. Okay, so now you can say that, okay, this solution. Now the question here, I use this identity. Whatever show up here, it turns out a Gaussian. Oh yeah. So now here, you have the identity. Okay, so then the green function of this problem, you can write it down as the identity. Okay, your major. And here, this is the phase length square over T, like this one. So here, this give you kind of this action principle. Okay, so now see here, because this one is in the numerator. So okay, so if this one is bigger, and this term becomes small, okay? And now here, say also that, okay, so this means the main contribution to this sum is due to when this path is the shortest from Y to X, okay? And also here, this major is defined the product. So this means that if you have too many refraction, okay, and each refraction coefficient is more than one. So you have too much refraction, this number becomes small. Okay, so this gives you the structural solution. This is equality. And now, with this equality, it allows us to take a differentiation. Okay, so now you can get the Lipschitz condition of this green function. Now, why I need to introduce this function? Because I want to look at the famous problem of the compressible Navier-Stokes equation about the well-posedness. Okay, so here this is a compressible Navier-Stokes equation. Okay, and say suppose the initial data is in the functional space of BV. Okay, it allows this continuity. So now you want to, okay, now there's a famous problem, okay, by the Adama. You want to prove your solution is a continuous dependence on your initial data. Okay, so now to define the continuity, we need to define the norm space. Okay, so now here our norm space is defined in the L1 norm. Okay, But okay, so now the statement of the well portionist is that if your initial data is L1 norm and the PV norm is uniform bounded, okay, and then you can prove that, okay, the difference of your solution is L1 norm is bounded by the difference of the L1 norm in the initial data. And this reason it can be worked out is because here, you read this one in terms of this U. It's a Higgs equation, and now you allow V has a sum as the PV structure. So then the equation we do it for Higgs equation is to allow us to control. So that means that by this formula, we can have some iteration procedure to construct the solution in the weak class. So now I just demonstrate to you that the green function with the precise structure is very important for you to solve the difficult problem. Okay, thank you.
Of the green function.
Yes.
So then there is after related to the decomposition of the resolvent.
Oh, yeah, okay. So this is the for the resolvent you need to see here. The resolvent you can write a quick case, okay, in the frequent domain. Okay, so that means you want to say actually to solve the resolvent as well, but you got the precise structure. So this means you decompose the resolvent into some part, okay, away from the origin. Okay. Some part away the origin, and then some part, you put around the exit. Yeah. Yes. Actually, this is the resolvent in the frequency. It decomposes at the frequency domain. Yes.
And then the singularity part is related to something like
Infinity.
infinity. The denominator have something like a single pole or something. This single pole gives us the dominant eigenvalue.
No, the singularity is not the pole. Pole is means eigenvalue. Okay.
Thank you very much.
是的，感谢各位贵宾聆听由世贤教授精彩生动的演讲。Thank you all for attending the brilliant and inspiring presentation by Professor 世贤游。欲提早到晚宴的同学可以移驾至乘车处。17点有前往晚宴会场的接驳车，待会将进行数学学会会员代表大会。预留下的老师与同学短暂休息后，请回到这间演讲厅。For students who wish to head to the banquet early, please proceed to the shuttle boarding area. Shuttle buses to the banquet will be available at 17. For the participants of the General Assembly of the Mathematical Society, we will resume here after a short break. Thank you.快没电了，所以我就把它留下来。像这个2头我也想换，不然我怕明天讲到一半会没电。电池
记得刚刚还有另外一只有拿过。
这边就4只而已。
哎，啊，这只有对吗？
这只要换电脑。哦，好。
2格的，好像我换一下，我换掉。
插电吗？
这边有没有电？这一格可以充吗？